Hi everyone, so we're moving on to linearization and linear approximations. So this is an application of derivatives, just like the mean value theorem was. Before we dive into what linearization is, we're going to just quickly look at this example up here, which just tells us that f of x is x squared, and they want us to find f of 2 and f of 2.1. This isn't anything that you don't know how to do. We're just going to substitute in 2. So we would get 2 squared, which is 4. Then if I asked you to evaluate f of 2.1, that's a little bit harder because 2.1 squared without a calculator might throw you off. Now, hopefully you agree with me when I tell you that it's 4.41. But doing it without a calculator can get a little messy. So that's actually where linearizations and linear approximations come in handy. Since a tangent line stays very close to the graph of the function when it is near the value at which it is tangent, we can use tangent lines to estimate function values. This process is called linearization, or really in other words we call it using a linear approximation. So again, what we're really doing is we're going to use this tangent line to get really close to function values without having to plug in nasty decimals. So let's look at what this looks like visually. So if we have f of x equals x squared, we're going to graph that first. So x squared is a parabola, so we know we're at 0, 0, 1, 1, 2, 4. Same thing on the other side. 1, 2. And we can draw our parabola through. Alright, now we know we want the equation of the tangent line at f of x equals 2. So we want to be tangent to the graph right here at 2. So let's see, that would be something like this. Alright, then it says approximate the value of f of 2.1. So here's f of 2. So f of 2.1, if I use my line, it's going to be right here. So it looks like it's a little bit above my actual function value, which is right about here, right? We're a little bit above it. Well, we said that it was supposed to be 4.41, so we're close to it, which is nice. Let's look algebraically at it. It's a lot easier to see algebraically. We can look on Desmos and see this actually play out and how close they can get on Desmos when we can really zoom in. So let f of x equal let f of x equal x squared. So it's the same function, write the equation of the tangent line at x equals 2. So we know if we're writing the equation of a tangent line, we need two things. We need the point and we need the slope. They're telling us it's at x equals 2, so my x value is 2. If I substitute that in, I know my y value is 4. And the slope of the tangent line we know just means find the derivative and evaluate it at 2. So if f of x is x squared, then f prime of x is equal to 2x, which means if I substitute a 2 in there, I get a slope of 4. So my tangent line then is y minus 4 equals 4 times x minus 2. Here's my equation of my tangent line. Now they're asking us to approximate the value of f of 2.1 using this tangent line. All that means is take this x value and substitute it in right here. So we're going to have y minus 4 is equal to 4 times 2.1 minus 2. Y minus 4 is 4 times 0.1. We know 4 times 0.1 is just 0.4. And then we can add the 4 over, and we get y is equal to 4.4. So what you need to be able to pull from that is that since we plugged this 2.1 into the tangent line, what this is really telling us is that f of 2.1 is approximately 4.4. And again, up at the top, we said that it was equal to 4.41. So we just estimated it to be 4.4. That's pretty close. All right, let's move on and look at some examples then of what this would look like on the AP exam. So we've got this table here. F is a function that's differentiable for all real numbers. We've got values of f and f prime on this interval. The second derivative has this property that it is greater than 0. We'll talk more about that later. Question 1, though, asks us to write the equation of the tangent line to the graph at the point x equals 1. Use this line to approximate the value of f of 1.2. Now, it doesn't have it broken up into two parts, but I am going to have you guys break this into a part A and a part B for me. So part A, we're going to go ahead and do what the question actually asks, which is write the equation of the tangent line. So again, we know if we need to do the equation of a tangent line, we need two things. We need a point and we need a slope. Let's see, equation line x equals 1. So 1, and I'm going to figure out my y value then is 5. So I'm going to look at the point, oops, no, -4. I looked at f prime. So 1, -4 is my point. The slope then is f prime of 1. That part there is actually 5, so our slope is 5. And we're going to go ahead and write the equation of the tangent line. So y plus 4 is equal to 5 times x minus 1. This is no different than anything we have been doing since we started talking about the equations of tangent lines. Now, let's take a look then at this next part where we're going to use it to approximate the value of f of 1.2. When they ask us to do something like this, they're going to ask us to change this the way that this looks. So I want you guys to put a part B here, and we're going to call this the linearization of x. So if you'll write that with me, linearization of x. All we're going to do then is instead of using y, we're actually going to use L of x. So we're calling it the linearization of x. All right, and what we're going to do is we're going to move that 4 over to the other side. So now we've got 5 times x minus 1 and then minus 4. So again, this y, all I did was swap it out for an L of x, and I took that 4 and moved it over to the other side. All right, this is actually going to be our standard form for linearization. So it's kind of a point slope form, but not quite. So standard form for linearization. So we're going to change it to an L of x instead of a y, and we're going to move that y value over to the other side so that L of x is by itself. All right, well now we're going to actually do what the question asked in this second part, which is use the line to approximate the value of f of 1.2. So we're going to then take 1.2 and plug it into L. So L of 1.2 is 5 times 1.2 minus 1 minus 4. So let's see, we're going to have 5 times 0.2 minus 4. And we know that 5 times 0.2 is actually 1. So we have 1 minus 4, which is then going to tell us that L of 1.2 is equal to -3. Now, this question didn't ask us to really plug in 1.2 into L. It asked us to approximate the value of f of 1.2. So we need to then acknowledge that that's what they wanted. So you need to say f of 1.2 is approximately -3. And that's our final answer there. All right, so let's look at some more. So we're going to do example 2 in class before you guys get started on some practice to make sure that you are solid on that. But we're going to move on to one more thing that we have to talk about in this video. So we just made an approximation of a function value. Now we need to start looking at whether these approximations are overestimates or underestimates. So how accurate are we in terms of these values that we're finding? So in order to do this, we need to look at the second derivative of the function. So we can determine whether our linear approximation will be an overestimate or an underestimate by looking at the second derivative of the function. This curvature is actually called concavity. Of the function, and it can be determined by examining this second derivative. So we've talked about how to take the second derivative, but we haven't really done anything with it, and this is where that is going to come up. So let's first talk about what it means to be concave up. If a function is concave up, then it looks kind of something like this. All right, a lot of times we'll tell you concave up, you should think about a cup. You can fill it up, right? And by the way, up and cup rhyme, so it looks like a cup that you can put stuff inside of. So anytime we talk about a function being concave up, what that means is that the second derivative, so f double prime of x, is positive. It's greater than 0. All right, so when you see the words concave up, this is what you need to think of. The second derivative is positive. And same going the other way also. If I tell you the second derivative is positive, you need to be able to understand that that means that the function is concave up. So let's think about what this means in terms of our linear approximations. We said we're looking at the slopes of the tangent lines, or that we're looking at tangent lines, to find these estimates. So if I draw a tangent line here, it doesn't matter where I draw it, but let's say I draw it here, or I could draw one down here, or I could draw one over here. Regardless of which one I pick, I can see that all of these tangent lines are underneath my actual function, which means anytime I have a function that's concave up and I do a linear approximation, it's going to be an underestimate. Again, this is because that tangent line is underneath my actual function. So any of these values that I'm trying to approximate are actually under the real value. Then let's talk about concave down. So if a function is concave down, it looks like this. All right, it's upside down, and it kind of looks like a frown. Do you get it? I made it rhyme again. So up, cup, down, frown. I know, I'm so creative, you guys. What would you do without me? All right, so if a function is concave down, then we're talking about the second derivative being negative. So f double prime of x is less than 0. That's what it means for a function to be concave down. So let's look at those tangent lines again. Let's see, if I draw a tangent line here, or if I draw one here, or even draw one right here, all of these tangent lines that I just drew are all above my actual function. So if we do a linear approximation with a function that is concave down, then that is going to be an overestimate. So let's think about what this actually looks like in a problem. So this problem here is the exact same one that we just did on the other page. Let me flip back and show you. It's the same table. It asked us for the same stuff. So on here we're looking for use this line to approximate the value of f of 1.2. That was what we did here. We said that f of 1.2 is approximately negative 3. So let's go ahead and actually write that. F of 1.2 is approximately negative 3. So we did that on the other page. We don't need to do it again. That would be silly. But now we need to figure out how can we actually decide whether this is an over or under estimate, and we need to justify our answer. That's very important on the AP exam. If they tell you to justify and you don't, they're going to stop reading what you wrote. So please, please, please make sure that you do that. Well, we just talked about how in order to decide whether it's an over or under estimate, we need to think about the second derivative. So if we look closely at this problem again, I kind of even told you guys earlier that there was this stuff about the second derivative that was going to be important. So this says that the second derivative of f has the property that f double prime is greater than 0 on this interval. So if f double prime is greater than 0, we said that that means the function is concave up. So if I were you, I would come down here then and draw a picture of a function that is concave up. And then draw a tangent line. And we can see that that tangent line is underneath my actual function, which means that this must be an underestimate. So we said f of 1.2 is approximately -3. This is an underestimate. Because the second derivative, so f double prime of x, is greater than 0. That's all we need for our justification. We just need to say how we knew it, and we knew because the second derivative was positive. So question 2 goes with question 2 on the other page. When we do it in class, we will then decide whether it's an over or under estimate, and you guys will get some practice done. I will see you in class. Thanks for watching.